Welcome to this session. Today, I'm going to discuss the method of Frobenius for the series solution of a second-order ordinary differential equation. And we consider a differential equation that takes the form d squared y by dx squared plus p of x dy dx plus q of xy is equals to 0. Now, provided that the functions p of x and q of x are analytic at all points, then the differential equation does not have singular points, and all the points are said to be the ordinary points of the differential equation. However, if there exists some singular points of p or q, then we shall call those the singular points of the differential equation. And that was discussed earlier. So in this session, I'm going to look at the method of solution, and I'm going to look at an example. Then we demonstrate the solution procedure using this example. So the differential equation we will be solving today will be the differential equation d squared y by dx squared plus x dy dx plus 3x plus 2 times y is equals to 0. Now, in this differential equation, we notice that the function p is equals to x, which is analytic at all points, and the function q is equals to 3x plus 2, which is also analytic at all points. So this equation does not have a singular point. All the points are ordinary points. So we notice that the point x is equals to 0 is therefore an ordinary point. This one is an ordinary point. So we assume a solution that takes the form y is equals to the summation from n is equals to 0 to infinity cn x raised to power n. We assume a solution of this form. So we're not going to find the first and the second derivatives and then substitute in this differential equation. So differentiating this function, we see that we get dy by dx being equals to the sum from n is equals to 0 to infinity n times cn x raised to power n minus 1. Now, looking at this function here, if we consider the case n is equals to 0, then we say that when you substitute n is 0 here, everything becomes 0. So the first term in this expansion will be 0. So I'm going to leave out that term, the 0 term, and you consider now the summation from the point where the non-zero terms begin from n is 1. So we have n cn x raised to power n minus 1. Now differentiating again, we get d squared y by dx squared is equals to the sum now from n is 1 to infinity n times n minus 1 cn x raised to power n minus 2. And again, we notice that the first term of this expansion, when we consider n is equals to 1, then the coefficient here becomes 0. So again, when n is 1, this will give us 0. So again, we can leave out the 0 term and start now the summation from n is 2 to infinity n times n minus 1 cn x raised to power n minus 2. So these are the functions to substitute. So we have the summation y is equals to the summation from n is 1 to infinity Cn x raised to power n. The first derivative is this, and then the second derivative. Our equation was d squared y by dx squared plus x dy by dx plus 3x plus 2 y is equals to 0. So we are going to be replacing the second derivative here with this function here, the first derivative with this, and y with this other function here. So this equation becomes, you see now the first term is this quantity here. So we get the sum from n is equals to 2 to infinity n times n minus 1 x raised to power, sorry, there is Cn x raised to power n minus 2. Then the second term we have x times the sum from n is equals to 1 to infinity. We have n times Cn x raised to power n minus 1. And the last term will be 3x plus 2. Then the sum from n is equals to 0 to infinity Cn x raised to power n. And the result, when we add all those terms, we get 0. Now, we see that we can simplify this. So we write the first term, n is equals to 2 to infinity, n times n minus 1, Cn x raised to power n minus 2. Then plus, for the second term, we see that we have x here, x raised to power 1. We should multiply x raised to power n minus 1. Then we add the powers to get x raised to power n, so that we have the sum from n is equals to 1 to infinity n times Cn times x raised to power n. In the next term, we can open the brackets here. So we have two terms. The first term we have 3x multiplying x raised to power n. So x raised multiplying x raised to power n will give us x raised to power n plus 1. So that we shall have 3 times the sum from n is equals to 0 to infinity. We have Cn x raised to power n plus 1. Then plus 2, the sum from n is equals to 0 to infinity. Cn x raised to power n. And the result here is equals to 0. This will be equals to 0. So the last two terms, the last term here, we have expanded this into 2. That is 3 times this, then 2 times that, which will give us the first term there, 3 times Cn x raised to power n will give us x raised to power n plus 1. 3 is a coefficient. Then we have 2. Now, with this series, we find that in order to simplify this, we need the powers of x in all the terms to be the same. So we choose to put the power of x as n. So we see that the second term and the last term, the power of x is n. But in the first term, the power of x is n minus 2. In the third term, the power of x is n plus 1. So we need to change these powers. So how do we change these powers? So to change these powers, we look at the first term and we can perform the following tasks. In the first term, here we replace n with n plus 2. So that in this case, where we have the sum from n, when we replace n with n plus 2, here, where we have n here, we put n plus 2. Then we get n plus 2, n plus 2 minus 1, c n plus 2, x raised to power n plus 2 minus 2. So we are replacing n everywhere with the n plus 2, so that this becomes, you see now, when we write n plus 2 is equals to 2, we can move to here. From here to here, we get, when we write n plus 2 is equals to 2, it's the same as writing n is equals to 2 minus 2, which is 0. So this becomes the sum from n is equals to 0 to infinity. Then we have n plus 2. N plus 2 minus 1 becomes n plus 1. Then we have cn plus 2, x raised to power n. So this is what we get as the first term. Now, we are not going to do anything to the second term because the power of x is n here. But for the third term, we see the power is n plus 1. We need to reduce this power to n. So we're going to replace n with n minus 1. So for the third term, I'll replace n with n plus n minus 1. We replace n with n minus 1. So see that we have the sum from n is equals to 0. So this becomes n minus 1 is equals to 0. So that term becomes 3. The sum from n minus 1 is equals to 0 to infinity. Then we have the coefficient cn, which we now write cn minus 1, becomes cn minus 1, x raised to power n minus 1 plus 1. So that this becomes 3. The sum from n is equals to 1 to infinity, cn minus 1, x raised to power n. So that our solution, our function, when we now substitute all these terms, you see now this term, the first term becomes what we have here. The second term remains. The third term becomes 3. The sum, 3 times the sum from n is 1 to infinity cn minus 1 x raised to power n. So when we do this substitution, on substituting back, we get the first term is the sum from n is equals to 0 to infinity, n plus 2 times n plus 1 cn plus 2 x raised to power n. The second term is not affected, so that one remains the same. Summation from n is 1 to infinity, n times cn x raised to power n. The third term now we have 3 times the sum from n is equals to 1 to infinity, cn minus 1 x raised to power n. And the last term is 2 times the sum from n is equals to 0 to infinity, cn x raised to power n, and the result is equals to 0. So we now see that the powers of x are the same in all the terms. The only problem now is the range of the summation. The first and the last term, the summation is from 0. The second and the third, the summation is from 1. So we can make the summation range the same by simply considering the first term separately. The first term here. In the first term, we consider the case n is equals to 0 separately. Then we sum from n is 1. Similarly, in the last term, we consider the case n is equals to 0 separately. Then we sum from 1 to infinity. So we see that in the first term here, if we consider the case n is 0, this will be 0 plus 2 times 0 plus 1, which is 2 times 1. So that will give us 2. And then here we have n is 0. So that will give us C2. Then x raised to power 0 is 1. Then the summation now, we can write the summation from n is 1 to infinity, n plus 2, n plus 1, Cn plus 2, x raised to power n. The second time we have the sum from n is 1 to infinity, n Cn x raised to power n. In the third term we have 3. The sum from n is 1 to infinity. We have n Cn minus 1 x raised to power n. And in the last term, where we have 2 times the sum from n is 0, we consider the case n is 0. So we have 2 times C naught, x raised to power 0 is 1. Then plus now the sum from n is 1 to infinity. We have Cn x raised to power n, and the result is 0. So we now have these terms. And we can consider now this term here. We add to this one. So we write 2C2 plus 2C0. Then the summation range is from 1 to infinity in all the terms. So we can put all the coefficients, n plus 2, n plus 1, Cn plus 2, then plus n Cn plus 3, n Cn minus 1, plus Cn x raised to power n is 0. Now, for the existence of this solution, all the coefficients must be 0. So at this point, we now equate the coefficients to 0. So first we have 2C2 plus 2C0 is equals to 0. And this will give us C2 is equals to negative C0. So we can write C2 in terms of C0 as negative C0. Then we equate the other coefficient here to 0. So we have n plus 2 multiplying n plus 1 Cn plus 2 plus we have here 3 there seems to be an error here. This one, the coefficient here was 3 times Cn minus 1. So there was no n here. There is no n here. There is no n here. This is just 3 Cn minus 1. So we have 3Cn minus 1. And then we have plus NCn plus 2Cn. And this is equals to 0. So I'm adding all this, I'm putting this coefficient to 0. So this is the same as writing n plus 2 multiplying n plus 1 Cn plus 2 is equals to minus 3Cn minus n plus 2 Cn. We say that these two terms, we can factor out 2. Sorry, we can factor out Cn to get n plus 2 times Cn. N plus 2 times Cn. So from there we can divide both sides by n plus 2 times n plus 1, the coefficient of Cn plus 2, so that we get Cn plus 2 is equals to minus 1 all over n plus 1 multiplying n plus 2, and this one multiplies n plus 2 Cn plus 3Cn. So once we have this, notice that this coefficient or this quantity is valid for the values of n starting from 1 all the way to infinity. So n should be greater than 1, greater than or equals to 1. N should be greater than or equals to 1. So we can write here this one is valid for n greater than or equals to 1, because the range of our summation was from 1. So we can now consider the case when n is 1. And if n is 1, we substitute here, we get C1 plus 2, which is C3. And this will be equals to minus 1 divided by, so our n is 1, so this will be 1 plus 1 is 2. 1 plus 2 is 3, so 2 plus 2 times 3 is 6. Then we have, in brackets, we have n plus 2, which is 3 C1 plus 3 sorry, I think there was a small error somewhere. 3 Cn minus 1. This was n minus 1. From here, 3Cn minus 1. So this is n minus 1 here. So when n is 1, n minus 1 is 0. So we have 3C naught. So that we get this is equals to minus a half C1 minus a half C naught. So C3 can be expressed as negative a half C1 minus a half C naught. Now, if we consider the case n is equals to 2, we come back here, n is 2. 2 plus 2 is 4. So we get C4, which will be equals to minus 1 divided by, now we substitute here, n is 2. So 2 plus 1 is 3. 2 plus 2 is 4. So 3 times 4 is 12. So we get 12. Then inside the brackets here, we get 2 plus 2, which is 4C2 then plus 3 C1. So we get 4 C2 but C2 is equals to negative C naught. We had seen that. So we can substitute and write C4 is equals to minus 1 over 12 into minus 4 C naught plus 3 C1. If you open the brackets, we get 1 over 3 C naught minus 1 over 4 C1. That is C4. Now, if we consider the case n is 3, if we consider the case n is equals to 3, then Cn plus 2 will give us C5, which will be equals to minus 1. The denominator here will be, if you look at our expression, n plus 1, this is 3 plus 1 is 4, 3 plus 2 is 5. So this is 4 times 5, which is 20. So the denominator becomes 20. Then we have n plus 2cn. So 3 plus 2cn, that is, will give us 5c3 plus 3c2. 5c3 plus 3c2. But c3 here, we have seen that C2 is equals to minus C naught and C3 is equals to minus 1 over 2 C naught minus 1 over 2 C1. So we can substitute this and get C5 becoming minus 1 all over 20. We have 5 all over 2 C naught. This is minus 5 all over 2 C1, then plus, or rather minus 3 C naught. So we can simplify this, and this should give us positive 1 over 8. 1 over 8 C1, then plus 11 over 40 C naught. We can continue like this to get C6, C7, C8, and so on. Our solution, remember, was y is equals to the sum from n is 0 to infinity, Cn x raised to power n. X raised to power n, which we can write in the expanded form as C0 plus C1x plus C2x squared plus C3x raised to the power of 3 plus C4x raised to power 4 plus C5x raised to power 5 plus and so on. So the terms are of that form. So we have the first term is C0. The second term is C1 times x. We have not obtained any value for C0 and C1, so we shall still write C1x. Then for C2, we saw that C2 is equals to negative C0. So where we have C2 now, we are going to replace with C0 minus C0 x squared. Then where we have C3, we obtained minus a half C0 minus a half C1. So this is times x raised to power 3. C4, we have it here as 1 over 3 C0 minus 1 over 4 C1. So we are going to write plus 1 over 3 C0 minus 1 over 4 C1 times x raised to power 4. Then C5 is 1/8 C0 plus 11/40 C1 So this is multiplied by x raised to power 5. Maybe you can check the signs for this. I'm not sure whether the signs were that. Yeah, the signs are all positive, because if we open the brackets here, we'll get the signs being positive. So we can now consider these terms, the terms with C0. So we have C0. So we have 1 minus x squared minus a half x raised to the power of 3 plus 1 over 3 x raised to the power 4 plus 1 over 8 x raised to the power 5, and so on. The terms will be of that form. Then C1, if you look at this, you see that the first term is C1x, so we have x. The next one we have minus 1/2 x raised to the power of 3. Notice that we don't have x1 c1 x squared. We only have a half c1 x raised to power 3. Then the next one will be minus a quarter c1 x raised to power 4. So we have minus 1 over 4 x raised to power 4. Then we have plus 11 over 40 x raised to the power of 5, and so on. So that this one is now the general solution. Y is equals to this, where C0 and C1 are arbitrary constants of integration. See that this solution can be expressed as C0 y1, a function of x, plus C2 y2, which is a function of x. In this case, y1 is this one is C1. This one is C1, y2, function of x. Where y0 is or y1 is this series, y2 is this series here. So the general solution is of this form. C0 and C1 are arbitrary constants of integration. I think there was some errors somewhere. I think there was some errors. When substituting this value here, this one was 1/8 C1 plus 11/40 C0. So this one was C1 here. And this one is supposed to be C0. So when we are substituting, when we are working out here, we have 11/40 x raised to power 5. So this should have been 11/40. And the term here is 1/8. This one should have been 1/8 x raised to power 5. You can make that correction. the substitution. We made an error when substituting here. I wrote C0 instead of C1, and then here C1 instead of C0. But basically that is the solution procedure. So you can practice this with other equations. So you note the procedure. First, once you identify that the point such as 0 is an ordinary point, then you write a solution to be of this form. Differentiate that, the first derivative and the second derivative, then substitute back into the given differential equation. So when we substitute back, ensure that the powers of x are the same in all the terms by using a suitable substitution here, as we have done here. Then the next thing is to ensure that the summation limits are the same for all the terms in the summation. Then next, equate the coefficients of the corresponding powers of x. That is, you equate the coefficients of each power of x to 0. Then obtain this kind of a relationship. Once you have that, then you can expand that for various values of n and obtain a general relationship. So basically that is the solution procedure. Remember, you'll be substituting back in this series. Write your series in the expanded form. Then C0 and C1, probably you will not have obtained any value for that. But from now C2, C3, C4, C5, and so on, substitute with the values that you get, then simplify. So basically that is the solution procedure using the series method.